Let's take a circle like this and place a coordinate plane over it. To find the area of such a shape, we could divide it into rectangles whose area formula we already know. But as you can see, rectangles don't fit the circle very well. There are empty spaces inside the circle, and the rectangles extend slightly beyond the boundary. If we reduce their size a little, you'll notice it already looks better. The error is decreasing. Let's shrink them even more. See? It keeps improving. If I make the thickness of these rectangles almost infinitely small, really thin, and then add up all their areas, I can actually find the area of the circle. Let's make them as small as dx. In mathematics, dx is used to represent an infinitely small quantity, so dx is actually an infinitely small change. Alright, now let's keep just one rectangle and erase the others. Let's see if we can find the area of this single rectangle. Let's say our circle has a radius r. The equation of such a circle is x squared plus y squared equals r squared. I already know the base of the rectangle. I need the height. For that, I have to express the circle as a function in the form y equals f of x. To isolate y, I can move x squared to the other side as a minus. Then, if I take the square root of both sides, I get y equals the square root of r squared minus x squared. Of course, there's a plus and a minus. The plus corresponds to the top half, and the minus corresponds to the bottom half. So the area of one rectangle is 2 times the square root of r squared minus x squared times dx, right? That's just for one rectangle. To find the total area, you integrate from minus r to r. We've actually calculated this integral before. In one of my earlier videos, I explained how to find the area of a circle. You can find the link at the top right. I'll refer you there for the details, and in this video, we'll focus on the sphere. To explain the logic of integration, I started with the simpler case of a circle. Now we'll apply the same method to a sphere. Now, watch carefully as the circle turns into a sphere. See how this strip, which was a rectangle in the circle, turns into a cylinder. This is a very important information, because the volume of the sphere is actually the sum of the volumes of all these cylinders, just like the circle's area was the sum of rectangles. So, what's the volume of this very thin red cylinder? We take the base area and multiply it by the height. The base area is pi times the square root of r squared minus x squared, all of that squared. And the height is dx, which means an infinitely small thickness. To find the volume of the whole sphere, we add up the volumes of all these infinitely thin cylinders. That's what integration does, going from minus r to r. Now, in this expression, the square root and the square cancel each other out. Pi is just a constant number, so we can pull it outside the integral. What's left inside is r squared times x minus x cubed over 3. When we plug in the lower and upper limits, we get something that looks a bit messy at first. Let's simplify it. Here, we end up with 2r cubed minus 2r cubed over 3. And that gives us the famous formula for the volume of a sphere, 4 over 3 pi r cubed. That's it. I hope the logic behind integration is clear now. If there's anything you didn't understand, don't hesitate to ask. See you in the next lesson.